Good morning, everyone. First of all, thank you for inviting me to present my some research topic on this conference. And thank you for the host and the hosting committee and all participants. So myself, Dr. Pandarasamy Arjunan. Presently, I'm working as a postdoc in a UC Berkeley Research Lab in Singapore. Today, I'm going to talk about explainable artificial intelligence. Due to the availability of limited time, I will present some overall concepts and what are the different tools available to enable explainable artificial intelligence. And I will also share some resources and the materials that the participants can go through later if they are interested in pursuing some research around explainable artificial intelligence. So before we get into what is explainable artificial intelligence, let's try to understand, how the traditional programming and how the ML or AI model works. So in case of traditional programming, so we have a computer to which we are giving some data, some input, and then we also develop some programs, some coding or using some standard programming languages like Python or Java, and the computer is going to give us an output. For example, let's say if you are writing a simple program to calculate a Fibonacci series. Okay, so you create the program to calculate the Fibonacci series, and you will give some data like, for example, I wanted to calculate the Fibonacci series for some value, let's say 5. And then your computer will, based on this program and based on this input, it will generate some output. Okay, what is that Fibonacci series? Now, whereas if we consider the model of ML, it's slightly different. So we are to the computer, we are going to give the data and the output, and this computer is supposed to generate the program automatically, right? So that's the main difference between the traditional programming and the machine learning paradigm. So here the computer is supposed to develop a program, right? Now let's have a closer look into how this program could be developed or could be modeled. So generally in ML notations, we denote the data or the output as Y, which is approximately equivalent to a function of X. So here the X is the data and Y is your output. This F is, instead of program, we call this F as a function or a model. So typically this model can be a linear model, or it could be a complex non-linear model like a deep learning network, or any ensemble model or anything. So let's try to understand this model bit in detail so that it will help us to understand what is this XAI and why it is important. So as you might have noticed, I have used this value approximate function because it's very, very difficult, or it's close to impossible to generate an accurate function or model that would reflect the mapping between the input X and the output Y. So instead, we will expand this equation with some error term. So basically, your output is a function of input plus some error. So typically, we call this error to measure this error only. We use a different evaluation metrics like accuracy, precision recall, or things like that. Now let's see a simple example. Let's say your Y is 120, and this function is that function we are supposed to come up with using some technique by the computer. Let's say your X or the input is 5. Can you guess what is this function would be? Right? So if you simply if you consider this could be a simple function called a factorial, because 5 factorial value is 120, and if we expand what is this 5 factorial, it's a multiplication of all numbers from that number 2 until 1. This is a very simple, and in which case there won't be any error, right? This is a very straightforward. Now let's consider another function. Let's say there is a function to which if you are giving an input value of 3.141, the output is 0. Can you guess what kind of function it is? So this function is actually a sine function. It is more complex than the factorial function that we have seen. But in this case, the problem is actually the value we will get the value we will get would be close to 0, and that is why I have introduced the term error here. right? So similarly, if we expand this, the both the previous functions are very simple functions. We are just giving a simple numeric value and we are getting some output value. Now let's consider a very complex function. Let's say for that function, your input is a collection of images, like maybe that image contain a dog or cat or any kind of scene in that image. Now you need to come up with a function that should identify, is there a cat in this in the given image, right? So we denote this function as cat, approximately a function of collection of input plus some error. This function could be a complex function that you can develop using some neural network model or any other standard machine learning or artificial intelligence techniques. So the reason I'm explaining all these things is actually, until now, what the focus is mostly on the accuracy of this, accuracy of the performance of these models. Now, what we need is actually, we need more than accuracy. We need to focus on how a human can understand the result from these functions or the models created by the computer program. So that is why we defined this term called XAI, and it is very important in recent days. I'll explain why it is important. So XAI is a set of processes and methods that allow human users to comprehend and trust the results and output. Let's say for the previous example, you have come up with some neural network model. Now you deploy this system to some novice user. Now that person is asking, yeah, this model is giving me some output, like whether it has a cat or something else. Now can you explain why this model or how this model is working, right? The purpose of explainable AI is actually, we need to provide some explanation how this model is working, so that the people who are using this model can trust the AI system, right? Now, the importance of XAI is actually, the XAI helps characterize the model accuracy and the fairness, transparency, and the outcome in AI-powered decision-making systems, so that people can start trusting this AI model. Now, the computer, as I said earlier, the computer model can be developed in various tools. You can develop a very simple model based on some statistical functions, or you can go with very complex models. Typically, these complex models are called nonlinear models. So there is a concept called white box and black box models. White box models are actually simple, that's based on simple statistical functions or some simple mathematical equations. So the models will be created. It is very straightforward, because we are able to, for example, for the same case with the factorial or the sine series, we have this series or we have this equation that we can understand, and we can explain, okay, yeah, this is a factorial series, and that is why we are getting this output. Yeah, this is a sine series, and that is why for the given input, we are getting this output, right? So these simple functions are based on standard statistics. They are called white box models, because that we can, based on the equation, we can understand that. Whereas the machine learning model or complex AI-based models are called black box model, because it is more focused on the complexity or the accuracy or the performance of these models. It's very complex. It's very difficult to explain, the intrinsic properties of, how the model takes the input, how it is passes from one, for example, in case of neural network, how the values are passed from one network into one layer into another layer. So all those things are very difficult to explain. So typically these complex models are called black box models. So the focus of XAI would be explaining whether it is a white box model or it's a black box model. So the model should be explainable. It should be explained in a way that a human or a novice user can understand, right? So let's say, how we are moving from a generic or XAI or MI model to an AI to an XAI model. So in case of for the same cat recognition example, so you have some training data and there is a learning process. Basically, you train your neural network model. After learning, you get this learned function or the learned model. Basically, in case of a neural network model, you will learn the weights for different layers or different neurons, and then the model is giving you some output like, yeah, this image contains some cat, and possibly, the probability value of this image having a cat is like, p equal to 0.93. Now, if the model is giving some output like this for a end users, so there are so many questions, right? We got the output, of course, but there are questions, right? People may suspect this model, right? So the first question is, why did this model come up with this value cat? Why not some other, maybe a dog or some other animal? Why not something else, right? That's what a user may ask. Okay, why do you succeed? That means actually why the model is actually able to come up with this number 0.93. Basically, that's a probability of saying, okay, this is a cat. Okay, and is there any instance this model would fail? For example, if you give a complicated image, whether this model will still able to recognize whether this is a cat or not, right? Now, by doing all these things, actually why the user has to trust this model, and if at all there is some error, how the user can correct this model so that it can provide the desired output. So this is the current scenario happening with typical AI system. But when we go forward with the XAI system, so basically we develop a lot of explainable model that should able to give an answer for all these questions. Okay, so when, for example, for the same AI system, the model is giving us the output like, this is a cat. Now it should be able to tell us, yeah, it has a fur, it has whiskers, and it has some claws, and it has these features like, 2 ears, maybe some different colors. And that is why the model is able to tell, okay, this is a cat, right? So all those features should be provided by an XAI system. And that's the thing that many researchers are working on, developing deep learning or any complicated models that should be able to give an explanation why the model has come up with a particular result and what is happening inside this model, so that people can understand and trust the system. Now, I'm not sure whether people have noticed from Nidhi Aayog also within India, there is an initiative called Responsible AI. The XAI is one of the key requirements for implementing responsible AI. So now, what is this responsible? These are all related concepts. Responsible AI is a methodology for large-scale implementation of AI methods in real organizations. And these models or this method should be fair and explainability, and it should be accountability. So point is actually there are many interesting things are happening around this XAI team or XAI research. And even the government is started initiating effort to make this AI system deployed in public places or some government agencies or any public services for the people. So all this AI system should be more responsible, and it should be do in a fair manner, and it should also take the accountability of the decision it's making. Now, the scope of XAI is actually the concept of XAI is an intersection of multiple disciplines. It's like it's an intersection of artificial intelligence, social science, and the human-computer interactions, right? So now let's see, there is a related term called interpretability and explainability. So these two terms are closely related to XAI, but there are some differences. So in terms of interpretability, it's the ability to explain or to provide the meaning in understandable terms to a human. So basically, to put it in another way, what is the degree to which a human can understand the cause of a disease, right? So that's the definition of interpretability. Whereas in explainability, it is associated with the notion of explanation as an, so this is a standard definition. To put it simple, how the AI or ML model arrived at the results. So for example, for the previous example, so if the AI model is, it's able to tell us, okay, it is able to identify there is a cat in the given image because it has, let's say, 2 ears, the face has 2 eyes, it has 4 legs, things like that. If it is able to, the system is able to not only give an accuracy of, okay, like 90% or 95%. In addition to that, it should also tell us that why the model is able to come up with that particular results. So that's the difference between interpretability and explainability. Now let's see what are the different. Okay. So now with the AI or ML, we have so many different models. So here is the relationship between the model's accuracy and their interpretability, how the interpretability of the models changes. For example, if we consider simple models like in a logistic regression or a decision trees, they are they are highly interpretable, and but their performance is compared to other models, its accuracy is it's relatively lower. But if we consider clustering based methods, mostly they are called unsupervised learning methods, and then we have like a support recognition and then ensemble methods, and then in the recently the deep learning or the neural network based models. So mostly the neural network based models are highly accurate. They are able to achieve better accuracy than other models, but the problem is they are not, their output is not at all interpretable. And that is why we need more XAI tools that can take the deep learning models as input, and it should be able to provide some explanation of the results it was able to come up with. Okay. Now there are some standard techniques and the concept related to XAI. So first thing is actually there are different categories of explanations the model can provide. So for example, it could be an intrinsic or a post hoc. Intrinsic means actually the model itself is designed in such a way that it can provide some explanation without using additional tools or additional analysis on top of that. Post hoc means actually you develop a model which is black box, which is complex, which is highly accurate, but you give this model to some different tool. That tool will understand this model's complexity and it will give you some explanations, right? So, and the another category of XAI is actually it's a model specific or model agnostic. So let's say you have come up with some XAI tool that can provide some explanation, and that tool could be specific. That tool can work specific to a particular model. For example, it can work only for the decision tree based classifier, or it can work only for the SVM based classifier, or it can work only for some particular ensemble learning methods, right? But there could be an other category of XAI techniques that could be model agnostic, so that you provide any kind of model, it should be able to come up with the explanation for the outcome. And the model could also be, the XAI model, XAI tool could be local or global. So local explanation is actually for a specific instance, for example, one image or one instance of a sample, or one for one input, it should be able to give some the explanation, or it could also provide an explanation for a collection of samples or all features, whatever that we have used as an input to train that model. Okay, so these are all broader categories of different XAI tools, and there are various techniques available in terms of implementing XAI techniques. It could be a very feature, it could be simple feature or variable importance. So this is a very standard method people are using so far to identify, okay, what is the importance of particular feature when predicting some outcome. And there is a slightly advanced method called partial dependence plots. I will explain these tools in a bit. And there is a tool called a LIME. It's called a local interpretable model agnostic explanation. As I said earlier, this LIME is a model agnostic tool, so that it can provide explanation for any model that you provide. Okay, and there is a more advanced tool called shape values, so that I also explain in detail. So now let's see what is this feature or permutation importance. So the way it works is actually in case of feature importance, that's a very standard technique. So typically, after you train the model, you will develop a feature importance plots that will tell us, let's say if you have 5 features used in a classifier or some regression model, it should tell us, okay, what is the the importance of each feature on predicting the output. Basically, what features have the biggest impact on predictions. Let's say if you consider a simple example of predicting the house price. Now there could be many factors like the square footage of the house, the location, the number of stories. So one of the dominant features would be the the bigger the house may have, higher price, right? So that's called a simple feature importance. So there is another technique called a permutation importance. So basically the decrease in the model score when a single feature value is randomly shuffled. So what would happen here is actually you take one feature, but you randomly shuffle the values within the set of samples you have. and then you see, how the model has performed, and based on that you will come up with the ranking, and that's what's showing on the right hand side. For example, this is a simple example. It is giving a weight for different features like a goal scored, distance covered, yellow card. For different features, when you try, all possible permutations for a particular feature by supplying the values, and then you calculate the model accuracy, you will come up with the score. So that's called a permutation importance. So based on this, you can tell, okay, so based on this different combinations, even when we supplying the values, still the model is doing, giving a better accuracy based on some certain features. So then you can say that, yeah, this feature is the most important feature. Now let's see the another technique. So this is called partial dependence plot. So what you do is actually for a particular feature, you consider a different range of values, and you see, let's say for the same house price prediction example, let's say your the square footage of the house is, let's say 0 to 100. When the values are between 0 to 100, now you see what is the effect on the prediction. Now let's say you consider a different range, like 100 to 200. 200 to 300, like this. You pass a different value range for a particular feature, and you see the outcome, and then you create a plot like this. For example, in this one, when the distance covered in kilometer, so the effect on the outcome is, it's getting increased after 100. So before 100 it's not increasing, and after 100 it is increasing. I'm not going into the details of all these things. So just give you an example of what all the different tools exist. For example, this is on the right hand side, you can see a 2D visualization of a partial dependence plot for two values. Basically, in the x-axis you see for a different goal scored, like a 0, 0.5, like this, and the y-axis you see this distance covers. So for a different range of values, you see this heat map showing that higher values when the distance covered is higher, and the goal scored is also higher. So like this, you can create a partial dependence plot for multiple variables, and you see which variable is having the higher impact on the final outcome. So these are all the simple techniques. This LIME, it's called a local interpretable model agnostic explanation. It focuses on training a local surrogate model to explain individual predictions. So there are some mathematics behind this tool. I'm skipping that part. So, but the outcome of this LIME tool would be, so it will give you some predicted value, and then for each predicted value, it will give you the features that is giving you a positive outcome or positive influence or the negative influence. For example, in this example, there are like 6 variables. That variable LStat, let's not get into the meaning of this variables, but the point is actually you'll get a visualization or the plot like this that will tell us these are all the variables that is having a positive impact on the outcome for a particular sample, and there are other set of variables that may have negative impact. And then based on this the LIME outcome chart, you will also get a feature value. For example, it is showing that for RM, it is the importance value is 5.83, and LStat is 8.47, like that. And then still more advanced technique called shape values. So basically, this shape value is it's coming from the game theory. So you calculate the outcome of a particular model by for a different range for a different combination of inputs, and then this shape values will provide the importance for different values. This is the equation. Again, I'm not going into the details. I'll share you some references where people can go through and understand this. But when you have shape values, if you pass a model, let's say for example, let's say a deep learning model or something to this shape values, it will give you the important segments within the image or the important values within the given data, which is which is making or which is more important to give the particular predictions. For example, if you see in this example, there is a egret. So there are different categories, right? It's whether this particular image is a crane or American egret. There are 4 flamingo. So you see there is a shape value behind. Wherever you have a positive that is denoted as red and the negative is denoted as blue. You see for the first example, there are more positive or the more red color related to this American egret. So basically, this model is going to predict the image. The bird in this image is actually American egret. So like this, for different categories, the shape values will generate the feature importance similar to a feature importance plot. And that based on that plot, we can understand, okay, so the model is able to give an output like, this is an American egret because, the features it has learned is looking like this. So, we can get a better understanding of, how the model works. And the bottom also, you see, this is something called a force plot. What you see is actually the values which is pushing the prediction to higher or on the left hand side, and which is pushing the prediction to lower or on the right hand side. So it is giving a value like, for example, this goal scored value of 2, it is going to push the prediction on the higher side. And that is why, the pink color portion is on the left hand side. So the point is actually when you apply these kind of shape value tools on top of any model, it will give you a set of plots. Based on that plots, we can understand how the model works internally. Okay. And there are some references. There are a lot of efforts by companies like IBM and Google are doing related to explainable AI. And there is an interesting book on interpretable machine learning. I have given this link, and interested people can go through that. And in Kaggle also there is a machine learning explainability short course, so that also people can go through. Thank you. If there are any questions, I'm glad to take it.
Any questions from participant side? Sir, I think no questions from the participants.
Okay.
Okay, sir. Sir, your session is very wonderful as well as it is on. I think it is a highly advanced, sir. Actually, you had given the that is the implementation concepts of those things, right, sir?
Yes.
Yes, it is very nice. And that about what is machine learning, what is artificial intelligence, everything you have explained it. Thank you, sir. Thank you very much for the nice sessions of explainable artificial intelligence. Thank you, sir.
Okay, thanks a lot. If there are any questions or people wanted to work on, related to the XAI, because I have worked on few topics related on XAI for energy management in buildings. And if anybody is interested, I'm glad to help them. And here is the link to my website, so where you can find more resources and people can contact on me.
Okay, sir.
Okay, thank you.
Thank you, sir. Thank you very much, sir. Participants, we have a break now around 12 o'clock. Again, we can join for the technical review. Around 12, we can start the technical review. That is the paper presentations. Around 12 o'clock, sharply come and join. Pandarasamy sir, you can leave.
நம்ம அப்ப ஸ்டார்ட் பண்ணிக்கவா இல்ல க்ளோஸ் பண்ணிடுவோம் மேடம் இப்போ?
Srinivasan sir.
சொல்லுங்க மேடம். கேக்குதா?
சார் நெக்ஸ்ட் வந்து 12 o'clock தான் சார் செஷன் ஸ்டார்ட் பண்றோம். இருக்கட்டும் சார், லைவ்ல இருக்கட்டும்.